Welcome to the final lecture that I'm going to be giving on this course. In the last lecture, we looked at the technique of life cycle analysis and saw an example of using life cycle analysis to determine the environmental impacts of a single polyethylene terephthalate fizzy drinks bottle. We also saw how life cycle analysis could be used to quantify all sorts of different environmental metrics. We played out a few different scenarios. We played out biomass substitution as a scenario. We played out recycling substitution as a scenario and saw that recycling can hopefully decrease global warming potential of plastic bottles production. More generally, if we can incentivise recycling, hopefully we can start to remedy an impending environmental disaster in terms of plastics pollution. But in terms of impending environmental disasters, the elephant in the room really has to be global warming. The seriousness of what is already happening cannot be overstated, let alone what is projected to happen. It is so serious that life on Earth as we know it could well be threatened. But there is some hope, and chemical engineers have a very big role to play in this. We're going to have a look at ways in which chemical engineering can assist the achievement of net zero, and we're going to be talking around ways in which we can decarbonise processes. We're going to be talking around carbon dioxide solvents, carbon dioxide sorbents, so the subject of carbon capture, which incidentally chemical engineers have been doing for over a century. We're going to be also looking at bioenergy with carbon capture and storage, and direct air capture. So let's start by reminding ourselves of some data. On my display, I have some recent atmospheric carbon dioxide concentration data. I say recent, it's only 2,000 years, which is barely negligible on a geological timescale. If we look at these data, we can see some interesting and alarming trends. First of all, we see that we have pretty much a slightly fluctuating baseline up until about 1750. That baseline fluctuates around 280 parts per million. After 1750, we see a very, very extreme rise in carbon dioxide concentration. Let's see how these data relate to global events. Now, correlation doesn't imply causation, but interestingly, the 1540 European drought coincided with a marginally higher level of CO2 in the atmosphere. Again, correlation doesn't imply causation, but between 1645 and 1715 there is a period of cooling on the planet, which was actually due to sunspots and decreased solar activity rather than carbon dioxide concentrations in the atmosphere. However, interestingly, the Maunder minimum does also correlate with lower carbon dioxide concentrations in the atmosphere. Bucking the trend somewhat, the 1757 European heatwave came around at a low carbon dioxide level. So we can see that in these three examples, slight fluctuations in carbon dioxide can correlate with globally observed weather events. Now, if we look from 1760 onwards, we start to see the birth of the Industrial Revolution. A lot of coal was mined, a lot of coal was burnt, a lot of CO2 was emitted into the atmosphere. And we can see a very, very significant rise from that 280 parts per million baseline up to, in your era, about 407 parts per million. That sounds a lot compared to that baseline. But in order to assess whether or not it really is a lot, we need to look far back into geological timescale. So, on my display now is the last 800,000 years on planet Earth. The last 800,000 years again is a small timescale on geological terms, but it tells us a very interesting story. Now, the line I'm putting up is the 2020 carbon dioxide concentration, 407, 408 parts per million. We can see that quite consistently for the last 800,000 years and longer, carbon dioxide levels were a long way below that. In fact, the baseline over the last 2,000 years is actually quite a high concentration in this data set. We're in the period known as an interglacial, a period between two ice ages. These fluctuations that you see in these data presented correspond to ice ages and interglacials. The low CO2 levels are ice ages, the high CO2 levels are interglacials, periods without ice. We are currently in an interglacial. So we are currently in an interglacial over the last 2,000 years, and we've gone and put the atmospheric CO2 level up to the highest recorded level in not only 800,000 years, but many million years. The last time atmospheric CO2 was at the concentrations we see today life on Earth looked very, very different to what we see now. So, carbon dioxide emissions are a huge pressing concern for our generation, and for your generation, and for the generation that will be your children. This could irrevocably change how planet Earth looks. So one of the things we need to do is to stop carbon dioxide emissions. We need to achieve what's known as net zero. So let's see how well we're progressing towards that at the moment. Let's take the dirtiest form of electricity generation that you can get, coal-fired power. What we're hoping to see is a phase out of this fast. So if you look at some of the data that's available in the public domain, you find that there is an increase in retired coal capacity. The y-axis is the electrical capacity in gigawatts, the x-axis is the year. So we can see that over the last 20 years, nearly 400 gigawatts of coal-fired electrical generation has been retired. This is good. However, over the same time period, 1,400 gigawatts of newly commissioned coal capacity has been built and operated, which is completely at odds with trying to achieve net zero. Not only is this bad, this is catastrophic. So if we look at the balance between these two, we can see that the net capacity change for coal-fired electricity production is a large increase, a 1,000 gigawatt increase, a terawatt increase over the last 20 years. These levels are starting to plateau. Hopefully, with the advent of net zero, the net capacity will start to decline. To put these figures in context, the total global coal generation capacity in 2020 is a little over 2 terawatts. In 2019, the global renewable generation capacity was about 2.3 terawatts. And so for the first time in a long time, first time ever, these two figures kind of balance. However, a lot more has to be done to reduce coal generation capacity in order to achieve net zero. So part of achieving net zero has to be CO2 capture. I can't see in the next 20 years 2 terawatts of coal capacity disappearing off the power grids of the world. We haven't even talked about natural gas, which is itself a CO2 emitter. So with coal-fired power stations, with gas-fired power stations being ubiquitous, we need to invest in carbon capture. So let's think a little bit about carbon capture. Now, chemical engineers have been doing carbon capture for a very, very, very long time. They didn't call it carbon capture, they called it acid gas capture. Because if you look at ammonia production, for example, carbon dioxide has to be captured in ammonia production because carbon oxides start to poison ammonia catalysts. Hydrogen sulfide is routinely removed out of refinery gas streams. It's called sour gas because hydrogen sulfide is a product of hydrodesulfurization of fuels. Hydrogen sulfide is another example of an acid gas. Acid gas removal is something that chemical engineers are very, very good at and have practiced for a very, very long time. Typically, the solvents used to capture acid gases fall into one of two camps. You have chemical solvents. Chemical solvents like amines are very, very good at capturing low partial pressures of carbon dioxide. The kind of partial pressures that you see in combustion gases, maybe 30 millibar to 300 millibar partial pressure. Chemical solvents, however, have a downside. Because they're very good at scrubbing low concentrations of carbon dioxide, they don't release that carbon dioxide without a lot of energy input. And so we talk about regeneration energy, the amount of energy required to release the carbon dioxide out of that solvent such that we can use the solvent again. And so the regeneration energy of a typical amine solvent, the benchmark amine solvent, is about 3.2 megajoules per kilo of CO2. When you think about this in terms of retrofitting carbon dioxide capture to a power station, this is a massive energy parasite on the electrical generation load. And so it's economically very unattractive. There are other solvents. There are physical solvents. Now, physical solvents are very good at capturing high partial pressures of CO2. So between 5 and 10 bar, you can use a physical solvent. For example, Selexol or Rectisol, which is refrigerated methanol. Now, you don't need to put thermal energy in to regenerate physical solvents. You just decompress them. Imagine, if you will, a fizzy drink and taking the lid off. All the carbon dioxide bubbles out. That's what happens when you regenerate a physical solvent. You reduce the pressure, the carbon dioxide is released, then you repressurize, and put back into your absorption system. However, the energy overhead here is the fact that these systems run at pressure, and so you need to compress gases up to that pressure, and you need to pump liquids up to that pressure. Because of the high partial pressures required for physical solvent systems are not easily retrofitted onto existing power plant. So new power plant is needed in order to use physical solvents. And so there's a lot of areas for innovation within the carbon capture arena, areas for innovation that will be explored during your era of chemical engineering. Firstly, there's solvent innovation. Can we have physical solvents operating at low CO2 partial pressures? Are there some clever molecules that can be developed that will allow us to do this? Or are there chemical solvents that can be designed with low regeneration energies? Liquid solvents aren't the only thing that you can use to capture carbon dioxide. There are solid sorbents you can use. Now, solid sorbents, alkaline materials typically, have been used again for over 100 years within chemical engineering. However, very new solid sorbents are being designed right at this moment in time. Metal organic frameworks are one of these. These are atomic-sized cages into which certain molecules can fit and be trapped. So, metal organic framework has a great application in carbon dioxide capture and could be a key paradigm shift in the technology. We also need new process technology. With these new solvents and new sorbents, can we design better energy generation systems that will allow us to use carbon dioxide capture at the right point in a process? Capturing carbon dioxide out of exhaust gas is arguably the worst place in an entire flow sheet to try and remove carbon dioxide. If we can get carbon captured at other points in the flow sheet, the process should be a lot more efficient and a lot easier to build with far lower capital overheads. There's also disruptive technologies. Are there enzyme-based systems that we can use to gobble up carbon dioxide? What other biotechnological approaches can we exploit in order to decarbonise our technology of today? Are there other physicochemical approaches that haven't been invented yet? And so when we look broadly at the area of innovation for carbon dioxide capture, there are many, many areas in which to work. I'd like to give you an example now of a high efficiency carbon capture scheme for power generation. I'm not going to go into the ultimate blow-by-blow detail of this, but the picture I want to paint is this. The green boxes are traditional power station operations. These are gas turbines, heat recovery steam generators and steam turbines. And so that's the sort of set of operations that you would see in a conventional gas-fired power station. This flow sheet has been adapted to run off hydrogen, however, hydrogen being sourced from synthesis gas. You already know a little bit about synthesis gas and how we can derive it. Steam reforming of methane is one source of synthesis gas. However, biomass is another source of synthesis gas. There may be also future sources of synthesis gas that could be very, very valuable. Now, the yellow boxes in this flowsheet are chemical process operations, and so in effect what we have is chemical plant coupled with power generation plant. What you do with the synthesis gas is make it into hydrogen. You've got carbon monoxide and hydrogen. You oxidise the carbon monoxide to carbon dioxide. The nice thing is typically this is done at elevated pressure in the first place, and hence the partial pressures of carbon dioxide tend to be high enough to use physical solvents. You then use physical solvents to capture that carbon dioxide, and then you depressurise these physical solvents to release that carbon dioxide into whatever capture scheme that you wish to put it. One of the neat aspects of this technology is that you don't treat the carbon dioxide in the gas phase. What you do is you refrigerate it, and you refrigerate it and liquefy it because there is part of the carbon dioxide phase diagram where liquid carbon dioxide exists. It is far safer, far simpler and far more energy efficient to pump liquids than it is to compress gases. Gas compressors are huge, expensive, semi-hazardous pieces of machinery. They're usually one of the most expensive bits of machinery you see on a plant. Pumps, however, are routine, safe, simple and cheap. So people don't usually talk about liquid CO2, but with liquefied CO2 you can use simple pumps to pressurise that carbon dioxide product for transport for its ultimate end use. You then feed the hydrogen from the chemical process into the power generation process, and you rob heat from the power generation process to power the chemical process. All the red lines are heat transfer stages coupled between the power plant and the chemical plant. And so one area for future innovation is high efficiency carbon capture schemes for power generation. There will be a bridging technology where these schemes are still needed until we have a means of successfully storing renewable energy for release onto the grids at times of low renewable energy generation. Now, if we're thinking of the biological production of synthesis gas, then a very nice thing to do would be to have bioenergy with carbon capture and storage. The photograph that I show on my display is of the Drax power station in the UK. Originally built as the largest coal-fired power station in Western Europe, this has now been largely converted for burning wood chip. The life cycle analyses that have been done on this show that this is a good way of reducing global warming emissions. But if you also capture the carbon dioxide that is produced from the combustion of wood chip and then do something with it such that it is not emitted into the atmosphere, then you actually have a carbon negative electrical generation plant. And so this could be one of the ways in which net zero can be achieved, decarbonisation can be achieved, but also maybe looking into the future, this is one way in which perhaps atmospheric levels of CO2 may start to be brought back in check once again. Another way in which we can start to bring CO2 levels back in check again is to maybe think about technologies such as direct air capture. Direct air capture is done already with plants, with forests, with anything that photosynthesizes. However, can we make machines that also do this? Can we suck air in, decarbonise that air with a solvent or sorbent that doesn't require much energy to regenerate, and can we then re-emit decarbonised air back into the atmosphere? It's a huge undertaking. It's going to be very, very energy intensive. At the moment, in your current era, there are 10 demonstration projects live that show that technically this is a possible thing to do. We're chemical engineers, we know that it's technically possible to do this. However, this process could use 25% of global energy production by the year 2100. If that global energy production is not already zero carbon, you go away and do the life cycle analysis and tell me whether this is a good thing or not. So this has to be underpinned by zero carbon generation, and the capture cost has to come down. Currently there's $94 to $230 per tonne cost for every tonne of carbon dioxide captured. In terms of context, rough crude oil price in August 2020 was about $330 per tonne. So carbon dioxide capture is cheaper than crude oil, but if we're treating carbon dioxide capture as waste remediation in a sense, people don't like paying for waste remediation. This is not an attractive set of economics. Also, we need to think of scale. To remove carbon emissions since 1850, we need to remove roughly 10 to the 12 tonnes of carbon dioxide out of the atmosphere. This is a vast figure, because if we consider since the same period, only 10 to the 11 tonnes of oil have been extracted since 1850. And so this needs to be done on a massive and global scale for it to have any impact whatsoever. So, let's think of a few key points. Chemical engineers have a pivotal role to play in achieving net zero, and chemical engineers have a pivotal role to play in addressing the challenges of decarbonising the atmosphere to pre-1900 levels. Part of this will be innovation in sorbents, in solvents, in novel capture technologies. Of course, part of this will also be within renewable power and renewable power storage, of which chemical engineering may again play a part. Underpinning any changes that are made has to be accurate life cycle analysis, so we can make sure that the changes we think we're making are the changes we're actually going to make.